So we're continuing on with Chapter 10, Section 3, and we're going to skip over a few here. I'm just trying to decide whether I want to give you some more problems. So actually I am. We're going to do 11 through 14. They're just so problem 14 asks the question, 11 asks the question, P810. Can you do this? Well, the answer is no. This number here always has to be greater than or equal to that number there, because there's no way that you can take 8 things and arrange them 10 at a time, because you'd have to have more than that. And the same applies for 12. So the answer is no. You can't do it. So 11. The question was, is it possible? No. 12. No. It says, explain how permutations and combinations differ. So permutations, this is 13, permutations are how many ways you can arrange a certain number of items where you don't repeat the items, and the order is important. So AB is different than BA. Whereas combinations, the order is not important, so AB would be the same as BA because it contains both A and B. It's kind of like set theory from the first semester. You know, the order wasn't important in terms of whether something was, sets were equal to each other, equivalent to each other. Whereas ordered pairs, the order is important. So that's the difference. And it says, explain how factorials are related to permutations. Well, what you're doing there is basically you're rewriting the fundamental counting principle. And if you have 6 things and you want to have them taken 3 at a time, then you start out with 6 items to choose from. Then you go to 5 and you go to 4, and then you've had 3 steps, so you've run out of things to do. And this is not factorial, but if you add this to both the numerator and the denominator, you know, the original thing relates to the fundamental counting principle. The other stuff are just added so that you can, instead of multiplying all these numbers out, you can just do 6 factorial divided by 3 factorial if you have a calculator that does that kind of thing. If you don't, then it really doesn't help you to write it in terms of factorials. Okay. And so what are we doing now? We're doing 17. Okay. So it says equations exercises 16 through 23 can be solved with the permutations, even though the problem statements will not always include a form of the word permutation or arrangement or ordering. So it kind of makes the problem easy because they're telling you to use permutations. But let's read them. It says, number 17 says, Tyler Onum, a contractor, builds homes of 8 different models and presently has 5 lots to build on. In how many ways can he arrange homes on these lots? Assume 5 different models can be built. So what he wants to do is to, he doesn't want to, do multiple models, same model for each lot. He wants to have them different because if you're living in the neighborhood, you don't want to have your house the same as the person next door. He has 8 different models, and it says assume 5 different models were built. That's the reason he's saying assume 5 different models, is so that we know that each lot is going to have a different model. Otherwise, you could still come up with the answer, but you would not be able to use permutations. So the key thing is, permutations has to have the number of available choices, which in this case is 8, and the number of slots that you're sticking into it. So it just becomes 8 things taking 5 at a time. And at that point, you can just use the formula to set it up. So permutation says you take this number to factorial and divide it by this minus that, the quantity factorial. So we get 8 factorial divided by 3 factorial. And 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 factorial. We divide by 3 factorial, so this part disappears, and then we just multiply that. 8 times 7 times 6 times 5 times 4 is 6,720 possible arrangements where order is important. Now, if the order was not important, then you would use combinations. So if you just want to use 5 different homes, but where they are is not that important, then you would take 8 things taken 5 at a time as a combination. And what you would do is actually you end up, it's basically the number of permutations. So it's the previous answer I got here divided by 5 factorial. It's whatever this number is, because if the order is not important, then I get rid of repeats that have the same choices but different different arrangements. And so I could just, that's not that many numbers, 6720 divided by 5 divided by 4 divided by 3 divided by 2 divided by 1 is 56. So there are only 56 possible arrangements if the order is not important. They didn't ask you that, but I'm telling you. Okay, 20. First, second, third prizes. So they're not saying permutations, but they're saying prizes. So it's important. They're awarded to 3 different people. If there are 10 eligible candidates, how many outcomes are possible? So again, because they're talking about prizes, we know it's a permutation problem. We know there are 10 people to choose from. That's the biggest number. And there are 3 prizes. And it says 3 different people. So that's the thing too, is if you had 3 prizes and you gave them all to the same person, then you would have a different result. You would actually have 10 times 10 times 10 would be the answer. Okay, so 10 things taken 3 at a time is 10 factorial over 10 minus 3 quantity factorial, which is 10 factorial divided by 7 factorial. And 10 factorial is 10 times 9 times 8 times 7 factorial, all divided by 7 factorial. That's 1. So just get 7 times 9, 10 times 9 times 8, which is 720. So there's 720 different arrangements. Okay. We're going to move on to combinations. Again, they say they're combinations, but you'll know that notice they are samples where you pick 5 things randomly. You don't care what order you pick them in. They're things, or they can be committees. So 25 is detecting defective cell phones. So it says if the shipment of exercise 24, and in 24 there were a shipment of 24 cell phones, contains 6 defective phones, how many of the sample size 5 samples would not include any of the defective ones? Okay, so this is a little tricky. So the way you do this is you think about it that if there are 6 defective phones, then how many good phones are there? So if you have 24 phones and you have 6 defective phones. So that means there are 18 good phones. And what you want, it says how many of the size 5 samples would not include any of the defective phones. So what you want to know is how many different ways can I arrange 18 phones. Again, the order is not important. I don't care whether I get a good phone, the same good phones in any order, just so I get the same amount. So in this case, because I'm talking about the good phones, I use the 18, which is the number of good phones, and those chosen 6 at a time. So that's the combination I use. In problem 24, it just said how many different ways can I sample 5 cell phones out of 24. There you'd use 24 and 5. Here we are, actually, it's not a 6, it's a 5, because we're picking a sample size of 5, so it's 18 things taken 5 at a time. So what is that? That's going to be 18 factorial divided by 18 minus 5 factorial divided by 5 factorial. So that's 18 factorial divided by 13 factorial and 5 factorial. So we get 18 times 17 times 16 times 15 times 14 times 13 factorial divided by 13 factorial. So these become 1. So we get 18 times 17 times 16 times 15 times 14 divided by 5 factorial, which is 5 times 4 times 3 times 2 times 1. 5 times 3 is 15. 2 times 4 is 8. So 16 divided by 8 is 2. So what I've got left is 18 times 17 times 2 times 14. So 15 went completely out. 16 became 2. And we end up with 18 times 17 times 2 times 14, 8,568. Okay, so let's do one more. And 29. So we have this guy, a contractor again. He's going to build 6 homes on a block in his new subdivision using 2 different models, the standard and deluxe. All standard and homes are the same, and all deluxe models are the same. How many different choices does Tyler have in positioning the 6 houses if he decides to build 3 standard and 3 deluxe? So what are we going to do here? I'm just going to pause for a second. Okay, so we're on 29. And it's kind of interesting. This one initially, I mean, it's an easy calculation, but trying to figure out what the heck we should be doing here. Because we think of houses as being the things that we're choosing, but in reality what we're choosing is the lots. So we have 6 lots. And what we want to do is we want to take 3 of those lots and place one type of house on it. So and it doesn't matter what order we're putting them on. It's just that we are going to. So the order is not important. That's why it is a combination rather than permutation. It's just that and because the order doesn't make a difference because they're all the same kind of house. So that's one reason why it doesn't make the order doesn't make a difference. So part A was you have 6 houses or 6 and therefore 6 lots. And 3 of those lots you want to have one type and 3 the other. So the first part of the problem is there's 6 things taken 3 at a time. And so that is 6 factorial divided by 6 minus 3 factorial divided by 3 factorial. So that's 6 times 5 times 3 times 4. The numerator, rewrite it as such. 3 factorial. 6 minus 3 here is 3, so we got 3 factorial and then 3 factorial. So these factorials cancel out. You could use, it doesn't matter which one you're canceling out. So, and then 3 factorial is 6. 3 factorial is 3 times 2 times 1, which is 6. So all we're left with is 5 times 4, which is 20. Now in the second part, part B, you have 2 deluxe and 4 standards. So there's really, you can do either case. You can do 6 things 2 at a time, which would be arranging the deluxes, or you can arrange the standards. And it turns out that these give you the same number. So let's just prove it's true. 6 factorial over 6 minus 2 quantity factorial times 2 factorial. And this one's going to be 6 factorial divided by 6 minus 4 factorial times 4 factorial. So this is 6 times 5 times 4 factorial. 6 minus 2 is 4, so you get 4 factorial. 2 factorial, those cancel out to become 1. 6 divided by 2 is 3, so you get 15 in this case. In this case you have 6 times 4 times 5 times 4 times 6 times 5 times 4 times factorial. I'm actually just going to 4 factorial because I have 4 factorial here, which I can cancel out again. And you see you get the same answer. And that's the thing about combinations. They're symmetric around this number. This will give you the most arrangements, and these are going to give lesser, but they're going to give you the same amount. So it turns out that if I did 6 things 1 at a time, or 6 things 5 at a time, those are going to give you the same answer. Okay, so that's that group of problems.